Well, anyway, good morning, everyone. I'm Lorraine. As I was introduced, I work here at UMBC occasionally. I work at home a lot. I work at Goddard sometimes. I'm a research professor here, associated with both the Department of Physics and Geography. And I have a lot of roles in the PACE universe. I'm the project manager. Not the project manager. I'm the instrument manager for the HARP-2 instrument. So I work with the people in physics on HARP-2, but I do my science with OCI. So I have kind of a split here. Let me start by asking a couple of questions. PACE, atmosphere, well, PACE encompasses a lot of things. Could you raise your hand if your primary interest in PACE is clouds? Yes. Andy, you have an audience. What if it's aerosols? Anyone primary? Good, that's more than I thought. And then ocean parameters of various kinds, most everyone. Okay, story of my life. I'm an atmospheric scientist. I happen to like both aerosols and clouds. And the point with PACE is that when PACE atmospheres is talked about, it's both clouds and aerosols. Aerosols and atmospheres are not synonymous. So I grabbed this picture from the PACE website. I thought it was really pretty, so I took it. What I'm going to do is, Andy said this is what we're going to do. We're going to talk about why study aerosols, what has been done up to now, and what can we expect from OCI. That's what we're going to talk about. Then there's the quiz at the end, because I am a professor here. So why study aerosols? This is where I always start. Now, I mean, people who come from an ocean perspective don't think about climate the way I think about climate, but I think about climate all the time. And this is a basic picture of climate. You have incoming solar radiation, and it gets distributed around. Some is absorbed by the surface, and you have outgoing long-wave radiation that some of it makes it out through the windows, and some of it is back radiated back down to Earth. And it's this balance of what's coming in and what's going out that creates the energy balance in our climate. And if things are out of balance, it moves in one direction or the other. And to start off with, here are the greenhouse gases that we all know and love and are in the news practically 4 times a day now. And what they do is they decrease the atmospheric window. They put more radiation back into the system, allow less to go out, and that's a warming trend, right? That warms the planet because you're trapping more heat into the system. But there's a whole nother side of this picture that no one ever talks about, and that's over here. And there's clouds and the atmosphere includes both the gases and the particles, which are the aerosols, reflect things back to space. So if you increase cloud cover or make the clouds brighter, or you add particles that reflect more light, you're going to send more things out to space, and that is a cooling, right? That offsets the greenhouse gases. On the other hand, some of this is absorbed by the atmosphere, right? So, you know, some aerosols are dark, and they absorb light, and so you're going to end up warming the atmosphere. So the aerosols always have this, are they cooling, are they warming? It goes back and forth, right? And if you get a picture like this is from MODIS, there's this smoke here, right? This is smoke from Portugal fires. And it depends if the smoke goes over a bright surface like a cloud, it darkens the scene, less radiation is reflected to space, and it's going to warm. But if it's over the ocean, it brightens the scene. The ocean's very dark. So now more light's reflected to space, and it's going to cool. So it's this game with the aerosols that has me attracted to aerosols, why I study them. Warming, cooling, all this complexity, how they get involved with clouds, how they change the cloud properties. And anyway, that's my reason for studying aerosols. I come from a climate perspective. But there's another thing about aerosols. People, animals, plants are breathing this poison. And it is poison because we know now that It's getting to be about a decade old, but the study came out that the single most environmental factor affecting human health is the particulate matter. Okay, so this is really, really vital. And in the United States, if you're from the United States, you'd stop worrying about it because we've killed practically every particle we've ever produced here. I mean, 30 years ago when I came to Maryland, it was like the sky was never blue in the summer. You couldn't breathe. It was always full of pollution. It's not like that anymore because of the controls that we've established. But other places of the world, it's just as bad as it used to be here. And then this, a lot of groups are starting to look at this. This is the particles come off from the continent, and it could be dust with all the minerals. Minerals are really yummy for plants. Or it could be smoke, and it gets deposited into the ocean, or it gets deposited on land, into the Amazon, for example. And it fertilizes the phytoplankton in the ocean or the tropical rainforests in the Amazon. And what we have here, and the groups who are trying to do this, let me warn you, this took us years to come up with this picture, years. The idea here is if a square is red, that means after a deposition event into that square, there's a positive chlorophyll response, meaning that there's more chlorophyll than there was before the event. And we're only looking at the top 10% of the events, and they signal this. And it doesn't matter where you are, if you're in the Dust Belt or if you're in this clean Pacific area. If there's more than normal aerosol that falls into that water, you're going to light up the chlorophyll. And it has different ways of manifesting itself. But this is not simple to do, and especially in 4 days. We can see. Anyway, why study aerosols? They're important players in the climate system. They affect the hydrological system through their effect on clouds, changing precipitation patterns. They kill people, and they fertilize ecosystems. Okay? Good. Remember this for the quiz. Well, what have we done up to now? I kind of made this chart. You can look at it. We had many different kinds of things in space, different kinds of sensors, different capabilities. There's no clock in here, Andy. Okay. We had multi-wavelength radiometers. This is like MODIS, which you're used to, but they were long before MODIS, like from the 1970s. There were multi-wavelength radiometers, and they were used to retrieve aerosol. We have ozone observing spectrometers. This is like TOMS, OMI. These are the things that found the ozone hole, right? But they also found that there's like a residue in the ozone retrieval, and that residue is related to aerosol. So they were used to look at aerosols also. Multi-angle radiometers, looking at the same spot from multiple angles, like MISR. Incredible amount of information coming from that. Multi-angle polarimeters, like HARP and SPECS now. And backscattering LiDAR, which is so essential, like Calypso. So essential and so rare. This is what MODIS can give you. Aerosol optical depth, which is the optical measure of the aerosol loading in the total column. And size parameter, when the surface is right. Over ocean, it's okay. Over some land, it's okay too, but we never made that a public parameter because a lot of surfaces use up too much of the information content to constrain to get a good parameter. UV aerosol index from the TOMS family. This is a really interesting parameter. It's, we're getting it from hyperspectral and UV, but we don't need hyperspectral. You just choose a few bandwidths there because the aerosols very smoothly across the spectrum. So all those wavelengths is just overkill for what we're trying to do with aerosol. But then you end up with two pieces of information. You get the loading, and you get the spectral response. That's all you have. But you have three sensitivities: how much there is, how absorbing it is, and how high it is in the atmosphere. So it was always a weird problem to try to get quantitative aerosol information out of this. People did it, and they did a good job, but you had to use a lot of assumptions, and the uncertainties were high. Okay, ready? Three sensitivities, two pieces of information. The multi-angle radiometers, like MISR, who could start providing more information, and they allowed the inference of aerosol type. You know, you could start to see different things. You could see things here, which they would call non-spherical. You can see spherical non-absorbing, spherical absorbing. You started to get more information about the particles with a multi-angle look. And then we had multi-angle polarimeter. We had it. It was Poldair. It was a beautiful instrument. There were three of them. Two had very short lifetimes. One lasted longer. And from that, you start to get a whole long line of things: single scattering albedo, real and imaginary refractive index. Really started to get down to maybe almost the chemistry of the particles that were being there. Like here, we have a parasol retrieval of single scattering albedo. That's the absorption parameter from the aerosol. And LIDAR. LIDAR gives us the vertical curtain, the vertical distribution of where the aerosol is in the column. Okay, what's been done up to now? We have a 25-year record of consistent monitoring of global distributed aerosol loading and qualitative size parameter. We have long-term, starting in 1979, okay? I mean, I'm talking long-term, not short, of a UV aerosol index with all its uncertainties. We have a global distribution of aerosol type from MISR, type, not chemical species. We have short-lived Poldair time series of globally distributed quantitative particle properties that you can only get from a polarimeter. And we have a 17-year record of aerosol vertical distribution and the identified features in the column. Okay? So that's what we have. And that's a pretty nice record. I don't think anyone should be embarrassed by this. This is a really nice record. So what can we expect from OCI? Going back to the Poldair parameters, we can get definitely AOD. We can get these kind of parameters over ocean, but we're never going to get stuff like this from OCI, these kind of detailed particle parameters. So does that make sense? So there's a limitation to what OCI can give you. But what we have from OCI is this beautiful broad range from the UV to the shortwave infrared that we've never had before on the same instrument. It's taking the multi-wavelength radiometer and combining it with the ozone observing spectrometer to create OCI. And this is what needs to be exploited to get all the information out of that instrument for aerosol retrievals. I've got 5 minutes, Andy. Okay, so it's like this problem we had with the three sensitivities and the two pieces of information. What if we came with the multispectral radiometer, which does the AOD really well? It gets the loading really well. That's what it does. And it does it spectrally. And we said, this is what the loading is in the UV. This is it. This is the AOD in the UV spectrum. So now I've reduced my sensitivities down to 2. And I can get absorption and the layer height from the UV channels. Okay, this is just the most wonderful opportunity. We're all following me, right? We got it? Okay. So this is what we call the unified algorithm, or the UAA, the Unified Aerosol Algorithm. And we read in the OCI data. We process the hyperspectral bands to match the lookup tables from our heritage algorithms. So we're only picking specific wavelengths out of that hyperspectral opportunity. We apply our heritage algorithms to get the AOD over land and ocean and the size parameter over ocean and sometimes over land. We extrapolate the AOD to the UV, and that was hard, but we're able to do it. We do some other things too that are innovative, I'm not going to talk about. We're actually using some machine learning to get that piece. We get these outputs, well, then we go through here, and then we modify our near UV heritage algorithm. This is coming from the TOMS and OMI heritage. We get that, we modify it to, we use identify the cloud-free pixels from what the other heritage has given us, because all the previous spectrometers for ozone, all of them were like 13-kilometer footprints, right? 7-kilometer footprints. They were giant footprints, and it was very hard to do the cloud cover retrieval, to cloud mask. 13 kilometers. You're always going to find a cloud in a 13-kilometer footprint. But now we have the finer resolution. We use that heritage. We use, in the cloud-free pixels, we get the OCI UV radiances. We obtain the AOD. We constrain the retrieval, and we get output the AOD, the size parameter of ocean, the single scattering albedo from the UV to the visible, and the aerosol layer height out of this retrieval. And for cloudy pixels, if there's sufficient loading above the cloud, we're retrieving the AOD above the cloud also, because there is enough information. Okay. I want to say it's not the hyperspectral capability that helps us. It's the broad wavelength range. This is unprecedented. It's actually the range at moderate spatial resolution because the UV never had that moderate spatial resolution. They're always 13-kilometer pixels. Here's some pictures that Karina made for me. This is showing this is actual OCI pictures. This is the aerosol optical depth. This is true color. There's this stuff coming off the coast there. It's very streaky. If you look at it carefully, it's very streaky. And we see these streaks in the AOD retrieval. This is the UV aerosol index. And this is aerosol layer height, these streaks. You can see them. There's some background lower aerosol, and then the streaks come out a little bit higher. And the single scattering albedo at one wavelength here. And there's global pictures that we can do showing this is AOD. You can see the AOD higher in this area. You can see in the single scattering albedo retrieved. And the first one was two different methods of doing it, which I'm not going to go into. And this is all coming soon. It's all coming soon. And I'm really sorry that it's not ready now. There's a couple of things. One, we have to get it into operations, which is taking a little bit longer than I thought it would. And two, OCI's UV calibration is still oscillating quite a bit. It's normal for a first-year instrument to have that kind of oscillation. So until we release it, I think we're going to wait until the calibration calms down. OK, here's our quiz. Raise your hand. Raise your hand. One reason to study aerosols. Yes?
They are important for climate change.
Climate change. Another reason. Yes?
Human health.
What's that?
Human health.
Human health. Anyone want to try on a third one? They're fertilizing ecosystems. Don't forget that one. Okay, what has been done up to now from satellite remote sensing? What have we do have now? I'm going to start calling on people. Anybody at the back table? What have we done from aerosol remote sensing up to now?
You mean as far as products goes, or?
What can we produce? What can we see from the aerosol right now? If we go to the web page, what does the web page give us about aerosols right now?
Things like Modus can give us aerosol optical depth.
Aerosol optical depth. That's a great answer. Angstrom exponent, the size parameter. From Calypso, vertical profiles. From Miser, aerosol type. And from the Tom's Tropomi kind of heritage, this UV aerosol index with its combination of absorption, optical depth, and height of the particle. And what can we expect from OCI? Are we going to be able to get chemical species? Are we going to be able to get complex refractive index? Are we going to get aerosol optical depth? Yes, good. What are we going to get that's beyond what we can get from Modus? Well, we could. My product's going to be 7 kilometers for a reason, but yes, you could. You're going to get single scattering albedo. You're going to get absorption from this. And you might also be getting aerosol layer height, as long as there's enough loading, right? So if there's real aerosol, you'll get the aerosol layer height. So that's the big difference. Okay, Andy.